Good morning, class. It's Mr. DeMarco. I got a couple emails about that last worksheet I sent out for Table F, the second part, doing the predicting if something is soluble or not in like dissolves like. So I figured I would give you a bonding review as well. That way you can help yourselves with your bonding notes and myself on this video to help you along with that process. Now, you have to remember that when it comes to bonding, there are three main types of bonding. We have ionic, we have nonpolar covalent, and we have polar covalent. And here again, I included the symbols that we use for each of the two different types of covalent bonds. In the phrase like dissolves like, if you don't know which ones of the problems you're looking at, that's going to pose the issue. So this video is going to review all three types of bonding and then how we can relate them to solutions. First, ionic. Ionic bonds, remember, ionic, ion means it's made up of a metal and a non-metal. When we're talking about a metal and a non-metal, remember that is going to be something from the left side of the chart, excluding hydrogen, and then something from the right side of the chart. That's what makes it a metal and a non-metal. Secondly, if it's a metal and non-metal and it's ionic, remember that we had the electronegativity difference. Electronegativity is the ability of an element to attract electrons. So on table S, if I remember, table S, back of your reference table, has the electronegativities of all the elements. If we look them up and subtract, remember that's what the triangle means, I'm going to get an answer between 1.7 and 3.3. When this occurs, we transfer electrons, and the metal loses the electron to become positive, and the non-metal gains to become negative. Now, in solutions, we don't need the bottom two pieces, and that's why I highlighted the first strip in red, because that's really all you need for solutions. If I see a metal and non-metal, it's automatically ionic all the time. But just for review, let's take a look at an example. Here I have magnesium oxide, MgO. If I go to the periodic table, Mg is on the left-hand side. It is magnesium, it's a metal, and oxygen is a nonmetal. So I know right away that Mg and O is a metal-nonmetal combination. However, just for review, let's go through the whole process. Mg is a metal, O is a nonmetal, and therefore, if I were to look up the oxidation numbers, Mg would be +2 and O is -2, and that's why when I swap and drop, I get MgO. But then I want to look at the electronegativity. Magnesium has a value of 1.3. Oxygen has a value of 3.4. So if I were to subtract those two values, because the triangle means to subtract, I'm going to get 2.1. And notice 2.1 is between 1.7 and 3.3, making it ionic. Again, easy to do as long as I see a metal and non-metal, but if I need to know the whole process, I go through the entire thing. Let's do another example. Sodium fluoride, NaF. Again, if I go to my periodic table, sodium is a metal, fluorine is a nonmetal, opposite sides. I know it's a metal-nonmetal interaction. But just to double check, we'll do the electronegativity as well. On table S, sodium is 0.9 and fluorine is 4.0. So if I have 0.9 and 4.0, my difference is going to be 3.1. Remember that my difference of 1.7 to 3.3 is ionic. So this would fall into the ionic category as well. Last of our ionic bonding examples, let's look at calcium chloride, CaCl2. Again, if I go to my periodic table, calcium is on the left, chlorine is on the right, therefore it's a metal, non-metal. If I were to look up calcium and chlorine on table S, calcium is 1.0 and chlorine is 3.2. So 3.2 and 1.0 are my electronegativities. And if I were to subtract, I get a value of 2.2. Notice again, 2.2 is in between the 1.7 and 3.3 that makes it ionic. Again, this is the entire ionic bond review, but we only need to really focus on the metal and nonmetal part for solutions. The second type of bond is covalent. Remember that when it comes to a covalent bonds are going to be made up of two nonmetals. So that means two things from the right-hand side of the chart, or H and something from the right-hand side of the chart. Now, when we have covalent bonds, it's important to understand that we're sharing the electrons. And because sharing's involved, again, as I said in class, just like people, I can share equally with people or I can share unequal with people. So that means in elements, the same thing occurs. If it's non-polar covalent, we have an equal sharing, a more stable interaction. If I have unequal sharing, it's going to be polar covalent bond. So for covalent bonds, we need to know the difference between these two sub classifications. Because again, if I'm dealing with like dissolves like, polar is not the same as non-polar, even though they're covalent. For these, it requires a little bit more effort in the bonding process. First, non-polar covalent. Non-polar covalent bonds are NPC. As we know, two nonmetals, okay? Has to be two nonmetals. As we know, they're sharing electrons equally. Now, that doesn't really help us when it comes to the solution chemistry. The nonmetals does, but I need to know if it's polar or non-polar. Here, my electronegativity difference is going to be 0 to 0.4. And here is where I have to draw out the structure. And again, this, you may have to go back to your notes and practice how to draw different Lewis dot diagrams to get the complete pictures. But if I draw it, and I will show you pictures in these slides, if it is symmetrical, which means that it's equal on all the sides, it's nonpolar. When I draw it out, if I look at the elements' charges using the periodic table, in a nonpolar covalent bond, all of the elements should have the same charge, okay? And you'll notice that in solution chemistry and bonding, the same examples always come up, which makes this a little easier to identify when we're dealing with certain questions. So let's move my face out to the corner and let's do an example. So CH4, okay? If I go to my periodic table, carbon is on the right and H is right here on the left, okay? It's, remember, a nonmetal on the left-hand side. So I know it's two nonmetals. Then I want to look at the electronegativity values. Carbon has a value of 2.6 and H is 2.2. So if I do the same thing that I always learn how to do with my electronegativity, I get 2.6 and 2.2. So if I subtract those answers, I get a value of 0.4. Notice that 0.4 is in this range. So I know I'm leaning towards my non-polar side. But to get the complete picture, let's look at the actual structure. There's one carbon and there's 4 hydrogens. So that means when I draw out my structure, this is what I'm going to get. Now, if we take a look, notice that all 4 sides of my drawing are equal to each other. That's what makes it symmetrical, right? Now, charges. If I go to my periodic table, remember H has a charge of +1 or -1 in some cases. But when I go back to my example, it would be a plus, a plus, a plus, and a plus. They're all the same. If I wanted to use the negative charge, it would be negative, 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 negative. And notice they're still all the same. So CH4 indeed is non-polar covalent. Again, a lot of work, but once you see it once or twice, you'll always know CH4 is nonpolar. That's not going to change. So let's take a look at a couple more examples here with nonpolar, just to see the process once again. N2. Obviously, it's N2, so that means there's two N's and they're both from the same side. That makes it, again, two nonmetals. If I go to electronegativity, that's going to be 3.0. So it's 3.0 minus 3.0 gives me 0. Notice 0 is in the range from 0 to 0.4, which makes it nonpolar. Now, this is the one that we did in class several times. And the special thing about N2 is that the only way the electrons can share in a stable fashion is if there's a triple bond. And notice in this diagram here, both sides are perfectly equal. If I go and look at the charge, N is minus. So I'm going to have a minus side and a minus side, which makes it equal on both sides in both items and in charges. So it's symmetrical as well, and again, makes it nonpolar. Last of our nonpolar examples is CO2. CO2, if I go to my periodic table, carbon and oxygen both from the same side, I know it's going to be two nonmetals. If I go to table S, carbon is 2.6, oxygen's 3.4, and I get a difference of 0.8. Now, CO2, if you can recall from our notes and our discussion in class, CO2 gives me a 0.8, which is a polar bond number. However, when I draw it out, and CO2 was another tricky one, it was a double bonded structure. Notice that both sides of the molecule are equal. Equal is nonpolar. Same with the charges. If I look at the charge for oxygen, because I'm looking at the ends, oxygen has a negative charge. So negative, negative, the sides are also the same charge, making it a nonpolar molecule. Okay. Again, when we're doing like dissolves like, we need to know, especially in the covalent field, if it's polar or nonpolar. That's why all this extra work is needed.